Hello, everybody. Welcome back. Guess what we're talking about? That's right, Poisson processes. This has been going on for a while, but very soon we're going to shift to a kind of related process called a birth and death process. And so this is going to give us a lot of good grounding for other Poisson processes. You're right. This is going to give us a lot of grounding we need to study more complicated processes. So a birth and death process is something where you have not a counting process, because that always counts and goes up, but it's allowed to go up and down. So you can think of your y-axis as a population size. And so the Poisson process is just kind of a pure birth process in that it can only go up. And if you think of, again, every time it increases as someone is born into the population, we are on our way to the more general birth and death process. So yay, us. Okay, so I'm going to share my screen. And this morning, the Tegu had a nice breakfast of scrambled eggs, mealworms, turnip greens, and a ground up quail sausage. Okay, so we have 3 definitions of the Poisson process, and I wanted to get them all written ahead of time to save time, but I only got one written, but I'm writing them very briefly. So definition 1, well, all of them revolve around a counting process. Definition 1 says we start the process with a count of 0, and the process at independent increments, and the increments of the process has a Poisson distribution. And definition 2 looks very similar. Here, I can even cut and paste here to get this done quicker. I always say cut and paste, when really I mean copy and paste. Okay, so I'm just going to change this out for a 2 and change out triple I. So the second definition is that the interarrival times are IID exponential. And of course, there's a third definition, and this is with rate lambda. There's a third definition, and I just wanted to emphasize that there's not a one-to-one kind of thing where clearly here, I from definition 1 implies I from definition 2. But in the triple I in all of the definitions, you may need a couple of these points from another definition. So here is definition 3, our little o definition. And it kind of looks the same. At time 0, we have a count of 0, and then our second thing is independent and stationary increments, and the stationarity came from triple I in both definition 1 and definition 2, but it doesn't from triple I here, so we have to impose that. And then the little o stuff. So we talk about a time interval of length h. It's supposed to be small. This is actually an asymptotic result, so as it goes down to 0, from the right, the probability of exactly one arrival in this tiny time interval is proportional to the length of the time interval. And the constant of proportionality is the rate of the process. So this is a lambda h, and then what we call negligible stuff. And then we have to talk about either the probability this is 0 or greater than or equal to 2. Either one would complete the definition. So I kind of like to use the one with the greater than or equal to 2 and say that this is just little o of h. And the reason I like that is it sort of reminds me of everything we do with continuous random variables. You know, you shrink the interval enough and you can't get an event. And in this case, you can't get a multiple event. And in fact, this goes to 0. So as you shrink the interval, you can't get 2 events, but it goes to 0 kind of fast. I mean, even this whole thing goes to 0 as h goes to 0. But this one goes to 0 faster, whereas this one is dominated by an h to the 1. The word for that. Okay, so we have proven almost everything, and we were in the middle of proving that definition 3 implies definition 1, and therefore definition 2. And I thought this was rather interesting because we get to go from little o's, almost nothing, to Poisson things. So this is for definition 3, triple I Actually, I might need the stationary and stuff. So I'm going to say definition 3 will give us definition 1 triple I. In other words, I'm trying to get the Poisson out of this. So we want to show that this increment n of t plus s, and this is a general increment, it doesn't have to be for a small s, minus n of s, this has a Poisson distribution with parameters lambda and t, lambda times t. By the way, I finally put the notes up for the last module, and it's a big update. So it includes a lot of this stuff from today. I'll be posting the video for today, but I'll be directing you probably to those notes from the last module. So in particular, we want to show that for any k equals 0, 1, 2 on up, we want to show that the probability that n of t plus s minus n of s is k. We want to show that this is e to the minus lambda t to the k over k factorial. So when we last left off, we were looking at proving this, and we were looking at the case where k is 0. So we started looking at the probability that, well, first of all, I want to consider a small time increment h. This is like the epsilon of Markov processes. It's always a small positive thing. So let h greater than 0 be a small time increment. And we looked at the probability that n of t plus h is 0. And so starting with that, we can write this as the probability that, so this is all the arrivals from time 0 up to some time t, and then a little bit higher than that. So the number of arrivals up here is there's many ways we can write this, but I'm going to write it as the number of arrivals by time t. So that needs to be 0. And then we need 0 more in that remaining little interval of time. And these are non-overlapping increments of time. So definition 3 does have independent increments in its double I. So by independent increments, this is the probability that n of t is 0 and the probability that n blah, blah, blah. Okay, so we have this equals this, and I'm starting with definition 3. So all I really know is what this is. It's one of these little o kinds of things. And so I'm going to recap this whole thing. We've got the probability that n of t plus h is 0 is the probability that n of t is 0. And then using our little o of h definition, this is 1 minus lambda h plus little o of h. And this is about where we were. So if you multiply out this right-hand side, you get the probability that n of t is 0. That's the multiplied by 1 term, minus lambda h times the probability n of t is 0, plus, so normally I just go ahead and write little o of h. That's kind of the point of this notation. I'm going to expand it just a little bit and say something that's little o of h times a probability. But there is no h here. So this is really a constant with respect to h, which makes this entire term just little o of h plus little o of h. Okay, so we have the little h, and we've got a t plus h and a t, and we're starting to see derivatives, especially if we move this to the other side and divide both sides by h. So we have the probability n of t plus h minus n, oops, that's not what I want, equals 0. minus the probability n of t is 0, and divide that by h. And on the other side, we're left with this term, but we have divided the h out. So I get a negative lambda times the probability n of t is 0. And I'm not finished, but I need to move this a little bit. And the O of h came along for the ride. And then I still have this term, but it is divided by h. If I multiplied little o of h by an h, it would still be little o of h. But a little o of h function divided by h may not be another little o of h. Little o terms do not always involve polynomials in h, but whenever they do, anything that has degree greater than 1 is going to be little o of h. And so this could be like an h squared, and when you divide it by h, now it has degree 1. It's just an h. And h goes to 0, but not as fast as a little o of h term. Because if you divide h by another h, you get 1, and that's not going to 0. So that's why I didn't just combine this stuff at the end into another little o of h. So I'm going to take the limit all the way across as h goes down to 0, all the way across. And what you're seeing over here looks like a derivative. Now, technically, it's called a right derivative because the h is only coming in from above 0, but I don't think we should talk about that. So use your imagination. It is a derivative, but really it's a right derivative. And we get the derivative with respect to t of the probability n of t is 0. And on the right-hand side, this has no h's in it, so it goes nowhere. So we get minus lambda, the probability n of t is 0. And then this last term disappears because any little o of h function divided by h goes to 0. That's the whole definition of little o of h. Okay, so you see a little differential equation. I'm going to divide this to the other side. I've got the derivative of this probability divided by that probability equals a constant, negative lambda. Perhaps you recognize this thing. I know I said at one point, oh, I'm solving a differential equation. Don't worry about it. We're not going to do very many. I guess we're doing another one. But I do maintain that I'm not going to ever ask you to solve a differential equation. I did for the grad students, but even then, I ended up giving you a solution that you can plug in. So if you integrate both sides with respect to t, then on the left side, the integral and the derivative undo each other, and you get the log of this probability. And on the right side, integrating a constant with respect to t, you're going to get that constant, which is minus lambda times t. I mean, I'm doing both sides from 0 to t. And a constant. A constant on both sides, but I really made one constant. So from this, we want to solve for the probability. And so I'm going to take e to both sides. And I get e to the minus lambda t plus c, which is, of course, e to the minus lambda t times e to the c. And so e to the c is just another constant that I'm going to call d. So my d is e to the c. And we need to figure out that constant. So what is d? I'm going to use single I from any of our three definitions. The probability that n of 0 is 1, because we always start the process at 1. So plugging in 0 over here, I get d e to the 0, I get d, and so this implies that d is 1, and so we have what we wanted. We have this probability is e to the negative lambda t, and if I take a little time to make it look like a Poisson, then hopefully you will see the Poisson. This is a Poisson with 0 plugged in. And that's what we wanted in the k equals 0 case. Okay, so I was going to do in class the k equals 1 case, and then point you towards the notes for a start on higher pace. But I think I'll skip it and you can read it in the notes. So the k equals 1 case, let me just start it for you. I would look at the probability that n of t plus h is 1. And I would also break up the interval from 0 to t plus h into the interval from 0 to t, and then the remaining little interval. So this is the probability that n of t, now that could be 0 or 1. So let's say 0 and n t plus h minus n of t is 1, or I get the disjoint event. So I get to add the probability that I already saw one event by time t, and then I saw no more events. So what I did, and you don't even have to read this if you don't want to, I think is really cool, but if differential equations are making you nervous, then don't bother. But these guys, this and this are independent, and this are independent. So I get to break up both probabilities into a product. This probability is the one I want to solve for. These two probabilities I can write in terms of little o of h, given definition 3. And this probability we just solved for in the k equals 0 case. So you plug that all in and you get a differential equation, or you get another differential equation. And the problem with this, going into this, is you need to use integrating factors, which is not bad at all, but now we're really derailing from Markov. So check it out in the notes if you want. Okay, so check out the notes if you want to see more of this, but I'm going to go on. What am I going to go on to? By the way, this all appears. Now the notes and the module numbers are off now. So this is all in the notes called 18, continuous time Markov chains, Poisson, but it happens to appear in module 21. Module, and not just or, and module 21, because that's where those notes are. Okay, so I have, usually at this point in this class, I talk about a lot of variations on the Poisson process, but because I don't really go on to use them for anything, I think it's kind of boring. So today I'm going to post notes on 4 different variations of the Poisson process. One of them is a marked process, which means that every time you get an arrival, you associate it, no, they do suck. You associate it with a random variable. So you can imagine maybe the random variable being a jump size. So you can generalize your Poisson process to say after an exponential amount of time, I jump up by a random amount. And so that's built off of a regular Poisson process, but then you attach to each arrival a random jump size. So that's kind of a cool one. There is a compound Poisson process in the notes, which is something that is conditionally Poisson. And this is all optional reading, but I will do the one that people have already asked me about, and that is the non-homogeneous Poisson process. So this is going to be our first example of a non-time homogeneous Markov chain, which I'm going to call NHPP. And so the non-homogeneous means that it's not time homogeneous. And this means, so my notation here is going to be a little off because we're talking continuous time. But remember at the beginning of class when we defined a Markov chain on discrete time, we had the probability that xn plus 1 is some j given xn is some I. If we had a Markov process, we denoted this was just our notation, a p sub ij. But at that time I said it is actually possible, it's still considered a Markov process if the p depends on the time n. So now p sub ij can depend on n. And I don't really want to decide on a notation for that because we're not going to use it. I don't want to use super n, right? That means something else, maybe of n, like a Pij n. I don't know. We're not going to need a notation. So if this Pij depends on n, but still doesn't depend on the further back history, it is Markov, but it's not time homogeneous. So I'm ready to define the non-homogeneous Poisson process. So the definition is we have a counting process, n of t. This is just something that increments by 1 every once in a while. And then instead of having a fixed lambda, we have, which is our rate parameter, we have a rate process. So we have a rate process or function, lambda t, which has to be greater than or equal to 0. And this is just our rate, but it gets to evolve over time. So we have different rates at different times, which is realistic, right? Even for my hiding in the bushes at the bank model, people are going to come in quicker around, 5 p.m. or lunch hours or before work, or I guess none of that applies anymore. They'll all be coming in on Zoom meetings while they're in other meetings pretending to pay attention. Okay, so that's the setup, but here are the axioms. I've got an I. It is that we start at 0. We never had to do this. It is a convention. But if we didn't start our Poisson processes at 0, remember, if we back up to what we were just doing with definition 3, that is going to affect the constant in the differential equations. Okay, so second, it has independent increments. That is the assumption, which may not be reasonable to you, but at least we're bumping our way more towards reality by saying that in 3, for all s greater than or equal to 0 and all t greater than 0, if we look at how the process increments between time s and then t units of time later, so n of s plus t minus n of s, this has a Poisson distribution. But the parameter is an integral. Sometimes people actually do this integral on the side and give it a symbol. It's an integral from s to s plus t of lambda of u du. So often people will use like a capital lambda, and they'll write it as an s or to s plus t, or sometimes they'll write it as an s and t as a function of 2 parameters. And either way, they mean this integral. So that integral in general is going to depend on s, which is going to make this not time homogeneous anymore. Unless, of course, the rate function is constant, or, I mean, if it's constant, right, you would just get back what we expect. So if lambda of t is lambda, then the integral of lambda du is going to be lambda t. We're going to get back the homogeneous Poisson process. No one ever uses that abbreviation, but I thought it would make sense in this context. Okay, so the interarrival times are, no, that's not true. This really, really, really messes things up. And it looks like I have an exponent there, which I don't have. Even though we have independent increments, the interarrival times are no longer independent. And they're certainly not exponential unless the rate function was constant. And there's actually not much I can tell you at all unless we have an actual rate function. So it becomes really problem specific. So I just wanted to say a couple of things. Note, this is maybe not obvious by staring at it, but we could show pretty easily that the interarrival times are no longer independent. And they're also no longer exponential, although they're kind of exponential looking. It's just that you get, in place of the lambda up there, you get an e to a negative like function of s to s plus t kind of thing. So, and you get something out front to make this a PDF, but it's not an exponential if this is not a constant times t. So it's exponential looking, but not exponential. And I think I put in my notes that I'm about to post, I actually derived the interarrival times in terms of the lambda function. So there's not much I could say without a specific rate function, but I can say that non-homogeneous Poisson processes are very, very difficult to work with. And what people tend to do when modeling things that do not have a constant rate, so customers coming into the bank and they come in faster in the mornings, and then there's a slow period, and then fast at lunchtime and whatever, people tend to just break up times into intervals over which they think the rate function is approximately constant. And then they do Poisson process stuff because we know so many things about the Poisson process. And I could talk about the Poisson process until the end of the semester. So there's even more to know about it with a constant rate. So people usually, it's not always appropriate, I think, but people usually deal with the non-homogeneous Poisson process by breaking time up into intervals where they think the rate function is approximately constant. Simulation of a non-homogeneous Poisson process, I think, is quite interesting. I'm going to state something right now that you will not make sense, and then we're going to take a simulation break, and after that, this will make sense. So simulation of a non-homogeneous Poisson process. So here is time, and here is a graph of my rate function. So here I've graphed lambda of t, not the actual Poisson process. This is not the counting process I'm graphing. So if you can bound this lambda of t by some constant lambda star, then, and we will show this eventually, but I thought this was a good segue into what we're going to be talking about next. Then you can simulate arrivals from a homogeneous Poisson process with rate lambda star, a regular old homogeneous Poisson process with rate lambda star, and that is a high rate compared to everything else. So things are coming in at a faster rate, which means you're going to have a lot of x's in here, a lot of arrivals. And then if you look at any particular arrival, so I'm going to look at the first x I drew, and I'm going to make a vertical line, then you draw a uniform random variable on this interval. So to do that, you grab a uniform 0, 1, and you multiply it by lambda star, and that makes it uniform on 0 to lambda star. Now, this is a real mess, but you're not supposed to come away from this slide being able to simulate this process. This is broad strokes. So multiply by lambda star, and that gives you something that is uniformly distributed on this interval. And then if it falls below the rate function, you accept it. So if your uniform falls here, then you accept this arrival as an arrival from your non-homogeneous Poisson process. But if it falls above the rate function, I want to say this goes away. I want to exit out, but there's way too many x's. So it goes away. So it's kind of like a moving, thinning kind of thing. And you can see that at least kind of the direction of things maybe makes sense, because whenever the rate function gets very low, you should not have a lot of arrivals. And that would correspond to not a lot of acceptances, because on all your vertical lines, the uniforms that you draw will have a hard time being all the way down here. So we'll talk more about this, but this is it wasn't as cool of a segue as I thought it would be. This is my segue to our simulation break. I have something in my head and it doesn't sound at all like I sound, which is awful. But there's this great song in my head when I sing that. Just so you know. Okay. It is a simulation break though. And this is our last method of simulation that is not Markov. And then we're going to do some Markov chain Monte Carlo simulations. So, and yes, this is going to appear on this homework. I've been putting off simulation stuff because there's still, up to recently, there were still people looking for languages. So this is already written up in the simulation notes, which appeared in a module a couple of modules ago. But if you go to the main Canvas page and go to the South Park thing, right under that, there's a link for the live lecture and the non-evolving notes. And then there's some simulation notes right there. And so in that, I wrote up the interval chopping method, the inverse CDF method, and this. This is the accept reject algorithm, and it's due to von Neumann. So people usually don't attribute it to him. Well, I'm going to write that there. So you're going to, if you look it up, you're going to look for accept reject algorithm. So why might you use this? Because looking in your arsenal, your toolkit of simulation algorithms, you don't have a method yet for simulating what you want. For example, suppose I want to simulate a random variable from a gamma distribution. I can't use inverse CDF method because I can't even write the CDF in closed form, much less invert it. Same thing for a normal, although I wouldn't use this procedure for a normal, although you can. Absolutely you can, but there's better things to do. Okay, so we have a target. I want to start using this language more and more. A target density, or PDF. And this is some F that we want to simulate from. Right, I'm going to use X for something else, but it's kind of like saying I have an X with PDF F, and I want to simulate values of X. Except I'm going to avoid giving it a name up here. I'm just going to say we have a target density, which describes the random variable we want to simulate. And this could be discrete or continuous. So I'm going to do my proof in the continuous setting, and possibly in today's homework, you might have to reproduce this proof in the discrete setting. Hint, hint. So it'll be a lot easier than this one because the continuous setting makes things a little weird. Okay, so here's what you need. So this is like pre-algorithm stuff. Okay, so you need, number one, you need a function g of x that is an upper bound for f of x. G of x is greater than or equal to f of x. For all x, no. Only for x in the support of f, which is, for all intents and purposes, all x. So if this PDF lives on 0 to 3, then you need a function g that is an upper bound for your function, at least on 0 to 3. And so usually I write that by saying for all x in the support of a function is the place where it's non-zero of f. So step one is you need to be able to come up with an upper bound. This is not a PDF because it's greater than or equal to f. So its integral is greater than or equal to the integral of f, and that is 1. But the integral here is greater than or equal to 1. If you can do it. And that's actually the second thing you need. You need this function to be integrable. I guess I have need up here, so I'll write g to be integrable. You need to be able to integrate it and get something finite. That's what that means. And the third thing you need to be able to do before using this is you need to be able to simulate values from the distribution with PDF h of x, which is going to be defined to be the g, but normalized. So 1 over c, g of x, where c is what you get if you integrate the g over the support of f, like over the region of interest. Okay, so if you have all that, so given where we are, if this is a continuous thing, the only way we know how to do 3, if so assuming you know nothing outside of this course, which I know a lot of you know a lot more than simulation than we've done so far, but our method, our only way to do 3 is the inverse CDF method. I will get to an example, it's not going to be today, where we're going to simulate values from the gamma distribution. And the gamma distribution has 3 distinct shapes depending on the value of alpha. And so a gamma alpha beta, when alpha is greater than 1, kind of looks like this. And trying accept reject and knowing that I only know how to use inverse CDF and really have only done this for maybe exponentials. You can think about an exponential distribution and then trying to find a constant to multiply it by so that it's always above the gamma distribution. And that would be your G. And we'll see that eventually. That was not worth saying. Let's prove that this algorithm works. So I want a proof of, I didn't give you the algorithm, only the pre-algorithm steps. So here is the actual algorithm. Step 1 is to simulate a random variable y from the PDF h. So if we were doing this for a gamma and we decided to bound the gamma by an exponential distribution that has been multiplied by something to make it high enough, then this would be simulating an exponential using the inverse CDF method. And then the second thing is you grab, draw, simulate. It's really simulate, but this is our basic unit from a random number generator. So you grab a uniform, a U, uniform 0, 1. And then the third thing is if the uniform is less than or equal to f of y over g of y. Now, the g is always greater than the f, so this number is less than 1 or equal to 1. So it kind of makes sense to be comparing a uniform to it. If that happens, you accept y as a value drawn from the distribution with the target PDF f. And I'm going to say just otherwise. So if the uniform is not less than or equal to that ratio, you delete everything and return to step 1, totally independent run of the algorithm. Delete everything and return to step 1. Meaning you reject that value of y. It's not something that's coming from the distribution you care about. So that part is the reject in accept or reject. Okay, I want to prove that if you do this, the accepted value of y has the target distribution, which was a PDF f. So because things are continuous, I'm going to do this proof using CDFs. In the discrete case, as you might be seeing coming up in your homework today, hint, hint, you don't have to use the CDF. You could go straight for the PDF. Okay, so that was my target. So let's prove this. I'm going to let X be the result of this accept or reject algorithm. And I'm going to look at the probability that X is less than or equal to some X. So I'm going to look at the CDF. I'm going to consider this probability. And what we want it to equal in the end is the target CDF. So what is the target CDF? This should be the integral from minus infinity up to x of the target PDF. Or if you want ahead of time, go ahead and give this a name. You can say, so F is the target, the thing we're trying to simulate from. That doesn't fit at all. And capital F is the corresponding CDF. Target, and let capital F be the CDF associated with that target. So what I've written here is the CDF of the random variable that comes out of the algorithm, and I want it to equal this. Right. Okay, so how do we get the random variable x less than or equal to x? Well, I am going to not condition on, almost condition on, but bring in another variable and marginalize it out. So I'm going to take the sum as n goes from 1 to infinity of the probability that x is less than or equal to x and comma, the first and really only except, because once you get the first except, you stop. But I want to make sure to emphasize is the first one is on the nth trial. So the first except has to be on either the first trial, the second trial, the third trial. These are disjoint events. So yeah, I can sum over those and get back to this marginal probability. Okay, in terms of the y's and the u's, this means, make myself some room here. This means the sum as n goes from 1 to infinity of a lot of stuff that I don't really care about. I'm going to write it as n minus 1 failures and comma, the nth y has to be less than or equal to x, and it had to have been accepted, which means the nth u is less than or equal to f of yn over g of yn. So the first except on the nth trial, we need n minus 1 failures. We need the uniform to be right, and we need the proposed value on the nth trial to be less than or equal to x so that the output is less than or equal to x. Okay, so these n minus 1 failures, these involve y1 through yn minus 1 and u1 through un minus 1. And I said it, but I didn't write it down specifically. But once you get to the end of the algorithm, if you reject, you erase everything, you start over, the y's and u's are independent of each other. And the sequences, like y1 is independent of y2 and u1 is independent of u2 and everything's independent. And so this part of the probability can be factored away from this part by independence. I'm out of time, unfortunately. So the next thing I'm going to do, I will have this written so we can start right at this line, is I'm going to try to compute this probability by conditioning on the value of yn. So I'm going to turn this into an integral of the exact probability that's written there, given that yn is y, and then yn is supposed to be drawn, no one can read that. And then yn is coming from the PDF h of y dy. So I'm about to write all of this stuff in here, condition on yn being y, multiplying by the PDF for y, integrating, and going. So we're actually almost done, but I definitely couldn't do justice to try to fit it in 20 more seconds or so. So in the end, we're going to end up seeing f of x. And if you can't wait, check it out in the notes. Otherwise, I'll see you back here on Friday. Thank you.